So the next question asks me why it is that the predicted probabilities are zeros and ones a lot. So I need to actually go back and look at what the probabilities are. So those are the probabilities. So you use type equals response, you get the probabilities. And if you look at them, so they're not like exactly zero, but this is a tiny, tiny number, right? It's like minus 5 times divided by 10 to the power of 16. So it has like 16 zeros after the decimal points. It's extremely, extremely small. And most of those numbers are extremely, extremely small. So why is that? So the intuitive answer is we're predicting using last name. And most people are the only people with their last name in the data set. So that means that the model can just exactly say, okay, we'll do the best job we can with predicting for you, which is, well, we know the answer, so we'll just either predict that you died with 100% probability or you survived with 100% probability. So the only people for whom you couldn't do that is people for whom there is more than one person with the same last name, where there is no certainty about how it'll go. So how would that look like mathematically? So let's look at kind of just some names, just randomly. So let's say that Crosby, this was like the one Crosby. This is actually the captain. So let's say that there was the one Crosby on the Titanic, and that Crosby did not survive. Right? We can actually check. So I'll just sort by the last name. So okay, so here we have, let's go with A. So we have one Abing, and Abing also unfortunately did not survive. We know that there was just one of him. So okay, so that means that when we're writing the model, right, we can say P of survived equals 1. So that's going to be equal to P logis of some A0, which we'll figure out, and then we'll say A. So this was Abing. Okay, A Abing times I Abing. And I Abing is going to be 1 only if the person's name is Abing. And then like plus like A Adams times I Adams, whatever, right? And this is only going to be 1 when we're predicting for Abing. And we know that when we're predicting for Abing, we just want to predict 0 because he did not survive. So what we can do is we can just make A Abing as low as we want. So it'll be very low, which would lead to P of survived equals 1. So low meaning kind of very negative. So that would lead to P survived equals 1 to be almost 0. So P logis, the value of it is never exactly 0 or exactly 1, but it can be very close to 0. So that's how it works out. So now we want kind of a theory about why the last name appears to predict survival, kind of beyond just saying, well, like if it's just the one person, then of course it's going to predict survival because we know the answer for that person and there's no constraint on the model just making this as negative as possible. Whereas, of course, if there are several Abings, you can't just make this one very negative because if one of them survived, you will be really wrong about them. So this only works if there is just the one Abing. So one possible experiment is to say, well, I mean, we'll just look at the people for whom there were more than one person with that last name, and we'll see if that actually still predicts survival. And one theory about why that might be is because maybe kind of all the families went together, and it's possible that it would be the case that the survival of family members would be correlated with each other, possibly because of class, but possibly because, so like there were all first class or second class, third class, possibly also because the families kind of stuck together and either kind of managed to survive or didn't all together. So how might we do that? So we need to construct a data set here. So here is one possibility for how to do that. So I'll figure out some names. So I'll figure out some names who will go in the training set where we'll try to estimate the probability of survival for them. And then I'll also have a test set with people with the same names but different people, and we'll try to predict for them. And the theory is that we're going to get something useful out of this because they're likely related. Okay, so here's what I'm doing. It's a little bit tricky. So I'll say group by last name and then mutate num equals n. So that is counting how many people there are with the same last name. So there's 2 people with this last name. There's just 1 person with this last name. That's possibly a mistake because here we have like Florence. So possibly actually there was another Bradley, but possibly not. So just 1 of those. So 2 Heaths, 2 Allens, 3 Morans. So okay. So now I'll just take the people for whom there's more than 2, or at least 2 rather, people with the same name. So that would go like this. So I filtered everyone with nums smaller than 2, so now all the nums are larger than 2. So now I'll just take the names where the name is the first one that appears in the group, right? So we have 2 bronze. So I'll just pick the first one. So that's how that's gonna go. So I just pick, so out of all the people with the same name, they're still grouped by last name. So I just picked the ones whose name is equal to the first name in that group, right? So I'll just pick the first person with that last name who appears in the data frame. And I don't have to, but I'll arrange by the last name so it looks like this. So I'll do the same thing with names test, except now what I'll do is I'll pick the second person in the group with the same names. So the names test and the name train are going to have the same names, last names, but they're going to be different people. Okay. So now what I'll do is I'll get the subset of the Titanic data frame which corresponds to people with those names, and I'll get the part of the Titanic data frame that corresponds to people with those names. So here I need to use something that we haven't actually seen, and that's the in operator. The way it works is like this. So this is going to be false, but if you have a 4 here, 4, then this is true. Okay. So basically, I'll filter and I'll say I only want people with names that are present in this vector of names. And that would be for the train set, and I'll do this for the test set. Okay. So now what I'll do is I'll fit on the train set. So here it warns that the algorithm did not converge. The reason is that it tried to make the probabilities really, really close to 100, but it couldn't and needed to stop somewhere. So it's actually fine. It's just warning us. So I can now predict for the train set. And I need to say path equals response, of course. And I'll say 0.5. And those would be the predictions for the training set. And now I can look at what the predictions for the training set are compared to what actually happened. So I'll say train set, because that's what I'm looking at, survived. And I expect a very high number, in fact 100%, because we just always have one each per, so we just have one person per last name, and we know exactly whether it died or survived. So now I can go to the test set and do the same thing. So I'll use the model that was fit on the train set, so it's predicting well on the train set, maybe not on the test set. So now I'll predict for the test set, and I'll compute the mean preds test equals to test set survive. And that's 67. So that's slightly better than the baseline, but not actually that much better. So most of what was going on is that the last name predicted well for people who were the only person with that last name.